Okay, my name is Vikas Raikar. I'm a principal applied scientist in Amazon pricing. So we're going to do the supervised learning part two, the summer school. So this is the agenda. So we're going to cover mainly four topics today. So the first one is around loss functions and optimization. The second is around evaluation metrics. The third is naive Bayes and k-nearest neighbors. And the fourth is support vector machines. The first two topics in general talk about which are applicable to all machine learning methods. And the second two are some specific instances of ML algorithms. Okay, we'll get started with loss functions. Yeah. So a loss function is essentially defined as a function of two things, right? So you have your true target variable y, and there is a prediction from a model which is y hat, and the loss is between y and y hat, and it captures the discrepancy between the true label and the model prediction. So in general, this defines your optimization objective, and it also mainly encodes our assumptions about the problem. And different loss functions result in different model behaviors. Today we'll be mainly focused on loss functions for regression and classification. So here are some of the most commonly used loss functions for regression. The first one being mean squared error, mean absolute error, and Huber loss. And for binary classification, binary cross entropy for multi-class classification problems, and also hinge loss, which is max margin loss used in SVMs. These are just some examples. These are not the only loss functions out there, but these are some of the most commonly used loss functions which we need to be familiar with. So we'll start with regression loss functions. The first one being the standard one, which is the mean squared error. The mean squared error is defined as one yi is your actual target, yi hat is your prediction. You take the square, sum over all the instances, and average it. Yeah. So MSE is differentiable everywhere. It also penalizes large errors quadratically because of the square term. And hence, sort of, it has one drawback, which is, we'll discuss it again going forward, is it's sort of sensitive to outliers, right? If you have a very outlier in your data, because of this penalty, the, the error due to the outlier dominates this loss function. So theoretically, this can be shown to be equivalent to the maximum likelihood estimator under Gaussian noise, right? So if you model y is equal to f of x plus epsilon, where epsilon is normally distributed with mean 0 and variance sigma square, then the maximum likelihood estimator will optimize this loss function, which is the mean squared error. So the second variant we're going to talk about is mean absolute error. It's sort of designed to handle this outlier sensitivity of mean squared error. As we saw, the MSC had this square error. So instead of the squared, we're going to replace it by the absolute value here. So because of this, it penalizes all errors linearly. So large errors are not disproportionately punished. Yeah. So as a consequence of this, unlike MSC, mean absolute error is robust to outliers. Similarly, we can show that the mean absolute error is equivalent to the maximum likelihood estimator under Laplacian noise. So y is equal to f of x plus epsilon. For MSC, epsilon was a normal distribution. Here, if you take the noise to be Laplace, then I think you can show that this MLE of this is equivalent to optimizing the mean absolute error. One thing to notice is that MAE is not differentiable at zero, but in practice we use subgradient or smooth approximations. Uh, a side note is mean square error optimizes towards the mean of the target distribution, whereas mean absolute error optimizes towards the median of the target distribution. The third loss, which we are probably more, we will discuss something called the Huber loss. Yeah. So one way to think about is Huber loss is somewhere a compromise between the MSC and MAE. Yeah. So you define a range called as a delta here, right? Where absolute value of y minus y hat is less than delta. If this error is within delta, then the Huber loss behaves exactly like mean squared error. y minus y hat whole square. If it is above that delta, then it actually behaves exactly like mean absolute error, where you're penalizing it as an absolute minus y hat. So you can see that for small errors, Huber loss is quadratic, ensuring smooth, fast convergence near optimum. Whereas for large errors greater than delta, it behaves like MAE, where it is linear and is robust to outliers. So one thing why Huber loss is preferred over MAE, because it gives you a control over delta, and also more importantly, it is differentiable everywhere. Yeah, and this delta actually controls the transition point between quadratic and the linear regimes. So here is a plot that illustrates the three loss functions: mean squared error, mean absolute error, and Huber loss. So the shaded area here is essentially the delta region. So this is your mean absolute error, and there is a mean squared error, and the Huber loss in the dark blue is in between this, where it behaves like MSC between in the shaded region, and it behaves like MAE outside the shaded region. Okay, so this is a summary of the typical loss functions we are going to use in regression. Most likely you're going to use MSC for most of your tasks, but if you think your task has a lot of outliers, then you probably prefer Huber loss function. So as a combination of the various loss functions, right? Most of this you already discussed, but we take one quick glance at the table here. Yeah. Okay, so the most commonly used loss functions for binary classification is what we call as the BCE, or the binary cross entropy loss. Yeah. So as earlier, we are going to take a loss function. We're going to average it over all the instances, right? Yeah. And yi here is your true label, which can either be 0 or 1. And p hat I is the probability that I is equal to 1. So this is your prediction from any of your model. For example, it could be logistic regression. It predicts what is the or a neural network, which predicts what is the probability that your label is equal to 1. Yeah. So the binary cross entropy is defined as yi log pi hat plus 1 minus yi log 1 minus pi hat. And there's also a negative sum here. Yeah. This is one of the most commonly used loss function for binary classification. So to build some intuition, let's take a look at a couple of examples, right? So let's assume that if the true label yi is 1, right? So if this is 1, then 1 minus 1 is 0. This term, the second term disappears. So the loss is essentially minus log p hat, okay? Or 1 by log p hat, yeah? So if the true label is 1, and if the model predicts p hat equal to 0.01, then the loss will be minus log 0.01, which is 4.6. Yeah. If it is 0.99, then the loss is minus 0.99, which is low, right? So essentially, the cross entropy loss heavily penalizes confident wrong predictions. So in this plot, the green line here represents y equal to 1. So you can see that if you predict, so here you know the true label is 1, so you'll essentially have your predicted probability should be greater than 0.5 and the loss will be less. But if you predict it to be more towards 0, then it kind of blows up here, right? And it gets you penalizes. As you get much lower, then it kind of explodes here, right? Similarly, the other way for y equal to 0. Yeah. So yeah, so the similar like other interpretations, you can start off with a logistic regression model, and you can show that this loss is equivalent to minimizing the negative log likelihood. Yeah. And the reason why it is called cross entropy is essentially this. So you can think of yi being 0, 1 as a true distribution, and p hat is the kind of the your predicted distribution. Then this is essentially, you can interpret in terms of the KL divergence between the true labels and the predicted distribution. Okay, so now the same one, we can generalize it to multi-class problem. It's a straightforward generalization. So rather than binary cross entropy, we're going to call it just a standard cross entropy loss for multi-class problems. Everything remains same here. So there is YIC, which is an indicator variable, which says 1 when the label is C, otherwise 0. And then PI hat C is the probability that the label is C. And this is defined by your softmax, which is exponential of Z by summation over Z, which you'll probably have studied in the logistic regression or the softmax classifier. Yeah. The other commonly used loss functions for binary classification is what we known as the hinge loss function. Yeah. So the hinge loss is a sort of a variant which is most popular for support vector machines. Yeah. So I think the best way to understand is it via this plot here, right? So the dotted line is what we call as the 0, 1 loss function here, right? So this is you get a loss of 1 and here the loss of 0, and this is sort of the y into f of x, right? The true label is 1 and what is f of x, right? So the direction has to be the same, right? So the hinge loss things, you put a buffer here, say, and then it's sort of upper bound on the 0, 1 loss function here. Yeah? So the loss is 0 when yi into fxi is greater than or equal to 1. So it's correct with sufficient margin. Yeah? So it's not differentiable at the hinge point here. And it also encourages a margin between the classes. It's also known that hinge loss encourages a sparse solution. Yeah? And this is sort of the equation for the hinge loss, where this equation of this one is max of 0, comma 1 minus yi f of xi, where yi is a true label and f of xi is w transpose x plus p, a simple linear SVM classifier. Okay, so till now we covered mainly all the loss functions for regression, mean square error, mean absolute error, and Huber loss. For binary classification, binary cross entropy loss and hinge loss. And for multi-class, probably the cross entropy loss functions. Yeah. So once you have the loss functions, the next step is you're going to find the parameters of the model that minimize the loss function. So we're going to talk about optimizations and various optimization algorithms to minimize the loss function. So now we're going to abstract it, right? We're going to look. So typically, for most of the problems, the loss function can be decomposed over instances. So in general, your loss function can be written as an average loss over each of the instances. So there is a loss of yi, that is the true label, and f of xi comma theta is what the model is predicting. And if I sum it over, I get the overall loss function. What I'm interested is in finding the parameters theta of the model f. So I'm going to minimize this loss function. Yeah. So depending upon the problem, there are broadly two schools of thought, right? So one is where you explicitly try to minimize it, write the equation, try to minimize it, and then write what is the value of theta. And with that, you get exact solution, but it's limited to certain standard problems, say like linear regression, where you can get an exact equation for the W parameters. Yeah. But these days, most likely, we don't use closed forms too much. Yeah. Essentially, what we are going to discuss in the slides. Yeah. So within the gradient descents, there are different variants we'll talk about. The which is essentially batch gradient descent, stochastic gradient descent, and mini batch gradient descent, yeah, which will be clear in the next few slides. So we'll start with the first one, which is the standard batch gradient descent, right? So mainly the core idea of gradient descent is, so you iteratively update your parameters. So you start off with some point Wt, and Wt minus 1 is your previous vector, and you're going to take a small step in the direction of the negative gradient. So delta L is, let's say I am standing right now at Wt minus 1. So this one is your gradient at that time step. So I'm going to move in the direction of the negative of the gradient. Yeah. And the step size is controlled by this learning rate called eta. Yeah. So the eta greater than called is the standard learning rate and determines the step size at each iteration. So we keep repeating this multiple times till convergence. Yeah. So roughly, if you think of it, it is that let's think of number of epochs. Yeah. You keep repeating it. For first, you compute the gradient of the loss functions. You're given your data set with respect to W. This is your DW, and you're updating W via W minus learning gradient to DW. Yeah. So why is this called as a batch gradient descent? Is that each step you're using your entire training data to compute the gradient. Yeah. So while this works, I think what happens is that for very large data sets, where in most of the time our data sets are huge, computing this gradient descent for huge gradient for this large data set is not computationally feasible. So this motivates what we the most popular algorithm called as the stochastic gradient descent. Yeah? So in general, most loss functions can be written, as I discussed, over a sum of the training instances. So in stochastic gradient descent, we update the parameters one data point at a time. Gradient descent, you need to compute the gradient with respect to the entire data set. But let's go to the other extreme that we'll just compute the gradient with respect to only one sample, right? One training example, right? This is what is called as the SGD. Yeah. So, and then you is a standard same gradient descent update formula. Yeah. So a complete A complete pass-through is called as an epoch. So you go over each epoch, then you iterate over all the examples. For each example, I compute the gradient, and then I compute the update via the standard gradient descent update formula. Yeah. So SGT is much faster and more computationally efficient, but the drawback is that we are approximating the gradient with respect to only one sample, and essentially it's a very noisy estimate of the gradient, and hence it can make to that it's the training sometimes cannot be stable, and it can lead to big oscillations that makes the training process highly unstable. So what is now commonly used referred when you refer to SGD is what we call as the mini batch SGD. Yeah. So we know that now using a single example results in very noisy estimate of the gradient. So we use a small random subset of the data called a mini batch of size B to compute the gradient. So this is essentially exactly like previous one, but rather than one example, let's use B examples. So you're going to, uh, one epoch is one run over the entire training data set. For each run, I'm going to iterate over multiple batches, get one batch, compute the gradient, and then optimize the gradient like this. So mini batch SGD is what is the most commonly used, and just sometimes we just refer to as SGD. Typical choices are B are like batch size, which you call as 32, 64, 128, 256, etc. So in practice, actually, for every batch, we also do a random shuffle of the data per epoch. Okay, so now I think from SGD, I think there is will not go in detail over all the variants, but there are more than several variants proposed which try to improve over SGD. The first improvement comes over SGD is sort of what we call as adding momentum term, where this helps us to make the convergence faster. The second kind of improvement comes where you have a different learning for each parameter. If you look at the previous update equations, eta is common across all parameters, but you can actually do a different learning for each parameter. And some common examples, popular examples in this style are the AdaGrad and the RMS Pro. And now the more modern ones try to combine both momentum and the different learning for each parameters. And these are the methods known as Adam W, muon, soap, etc. Yeah. If you take one away now, right now, the most popular SGD algorithm is Adam W or maybe Adam, yeah, which combines both momentum and adaptive learning rate. Along with these kind of improvement, there is something called as a learning rate schedule, which is essentially where as I mentioned earlier, you're doing over a batch epochs here, right? So you start off with a certain learning rate, but for every epoch, you start off reducing the learning rate according to a given schedule. And cosine annealing is a commonly used learning rate scheduler. Okay, so we covered loss functions and then we covered optimization algorithms. So now we're going to move towards a little bit our evaluation metrics. Yeah. So the way to Okay, so there are two things to look at. A loss function is generally not an evaluation metric, right? So a loss function is typically to help, used to train our ML model or estimate the parameters theta. And the loss function defines our what is our optimization or criteria. Yeah. And typically loss functions are differentiable, right? While we could use loss function to finally report the performance of the model in the test set, sometimes our actual metric is slightly different from the loss function, right? And this is where our evaluation metrics comes into picture, right? So the loss function training object does not necessarily be equal to the evaluation metric. Yeah? Some of the loss evaluation metrics we'll discuss right now are accuracy for classification or accuracy, precision, recall, F1, ROC curve, PR curve, and the area under the curve metrics for both ROC and PR. And for regression, we're going to discuss root mean square error, mean absolute error, and R square. So the standard way to look at binary classification errors is via confusion matrix. Yeah. So I think let's take a look at the table on the right here, right? So there is an actual value and the predicted value. The actual value can either be 1 or 0, positive or negative. And the predicted value can be either 1 or 0, which is positive or negative. So this gives rise to four classes of errors or true things it can be do, which are known as true positives, false positives, false negatives, and true negatives. Yeah. So maybe it's one way to remember is whatever is true positive is a correctly predicted positive. True negative is a correctly predicted negative. And the cross terms are the errors. A false positive is incorrectly predicted positive. So you're predicting it as positive, but it's false. And a false negative is an incorrectly predicted negative. That is, you're predicting it is negative, but it happened to be false, right? So TP and TN are your correct predictions. FN and FP are your errors across. Yeah. So based on these four things, you can define your error metrics. So the derived metrics, the first one is accuracy, right? Among all these four, what are the correct predictions? That is TP plus TN divided by the counts of all the four. The other two metrics are precision and recall. Precision is true positives divided by true positives plus false positives. That is, of all the predicted positives, which is TP plus FP, how many are correct? Yeah, so how precise you are. Recall is TP by TP plus FN, where of all the actual positives, how many were you able to correctly predict, right? So both precision and recall, if you look at it, the numerator is your predicted positives, right? True piece, how many of them are actually predicted, but the denominator differs. Denominator of precision is your predicted positives, whereas the denominator for recall is your actual positives. There's also one other metric which people use which is the harmonic mean of precision and recall, which is also called as F1 score, which combines both of these, which is 2 into precision into recall divided by precision plus recall. So one thing is now, I think little bit, I think it's not very clear from this slide is typically when you start off with binary classification, right? Uh, let's take linear regression or, no, sorry, logistic regression or SVM. For example, logistic regression, you say predict what is the probability that the label, right? Let's say 0.5 is a commonly used threshold. Otherwise, you're going to predict the label is 0. But this notion of 0.5 is arbitrary, but you can actually change your threshold to 0.1 also or 0.9 also. And changing this threshold theta gives you various trade-offs in terms of precision and recall. Yeah. So adjusting the threshold changes precision and recall, right? If you increase the threshold, you get higher precision and lower recall. And if you lower the threshold, you get lower precision and higher recall, right? So that's always, and this depends upon your domain and the problem, right? So it depends on the problem statement. For example, if you're in the domain of spam detection, right, where false positives are costly, you may want to prioritize on precision. But let's say you're doing a cancer screening or fraud detection where false negatives are costly, then you may want to focus on recall, right? And if you really cannot make a call, then probably you would use F1 score, which balances precision and recall. Yeah. So as we discussed, I think precision and recall depends upon the threshold theta. Uh, so one way to sort of quantify the behavior of any model which independent of the threshold are what are called as this ROC curves or PR curves. Yeah. So an ROC curve, also known as a receiver operating characteristic curve, it plots a true positive rate on the x-axis, the y-axis, and the false positive rate at x-axis for all thresholds, right? So you start off with one threshold, you compute what is the TPR and FPR, and you sweep the threshold from 0 to 1 or 0 to infinity based on your model. And then you can trace out a curve. This is called as the receiver operating or the ROC curve. And this one, the area under this curve is also called as the AUC. And AUC is essentially can be another metric to quantify the performance of a binary classifier, which is independent of the threshold. So in this plot, I think the dotted line, the diagonal is essentially a random classifier, and this blue dot is a perfect classifier. The random classifier will have an AUC of 0.5, whereas the perfect classifier will have an AUC of 1. And the better the classifier, more the AUC will be towards 1. Like TPR and SPR, we can instead of that, we can also plot the precision recall at all thresholds, and this gives rise to what is called as the precision recall curve, where we plot the recall on the x-axis and the precision on the y-axis, and the concepts remain the same. Yeah. And the area under the PR curve is now called as the PRAUC, whereas the area under the ROC curve is called as the ROC-AUC. So practically, I think when your classes are balanced, you'd prefer to use ROC, but if you think very highly imbalanced, people use the precision recall curves. Yeah. Or when you want to focus more on positives, you prefer PRAC curves. Okay, so till now we discussed mainly the evaluation metrics for classification, which happen to be like all this TPR, FPR metrics, F1 score, precision recall, and then their curves, the the PR curve and the ROC curve, which give you a threshold independent kind of a characterization of the performance of the classifiers. Regression metrics are fairly straightforward. So I think it's sort of also almost equivalent to the loss functions. So the first one is the root mean squared error, which is the squared root. Yeah. Second is the mean absolute error, where you take the mean of the absolute error. And there's also something called as the goodness of the fit, which is the R squared, which is considers the portion of the variance explained by the model. Yeah. Okay, so till now we covered three topics. We covered the loss functions. We covered various optimization routines to minimize the loss functions. And then we covered the actual evaluation metrics you would evaluate to report the performance of various classifiers and regressors. So then in the remaining time, we'll briefly touch upon a few simple classifiers like naive Bayes, k nearest neighbors, and the support vector machine. Yeah. Uh, the naive Bayes is a very straightforward, one of the simplest classification algorithms that you can think of. And it's a straightforward application of the Bayes theorem for classification. So let us think that X is your feature vector and CK is your class label, right? What I'm interested in predicted is given the feature vector X, what is the probability that this instance has the class CK? Using Bayes theorem, I can decompose it into invert it like this, which is probability of X given CK into probability of CK divided by probability of X. And here, this X is like a normalization factor which does not depend upon CK, right? So we can sort of remove it. So this is proportional to probability of X into CK into P of CK. So P of CK is your prior, the relevance of each of, what is the prior occurrence of each of the classes? What is the probability that you see class 1, class 2, class 3, right? If you have 100 instances, if there are 10 out of a class 1, 10 out of 100, 60 out of 100, and 30 out of 100 would be the, or 0.3, 0.7, 0.1 would be your prevalence, which you can get from the training data. So now we want to calculate, this is what is called as the likelihood, which is probability of X given CK, right? So if I have given the class CK, how are my features distributed and what is the model for it? The reason why it is called naive Bayes is because it makes a very simple assumption, which is called, it says that features are conditionally independent given the class. If there are D features, you make the assumption that all the features are independent for a particular given class. Hence, you can factorize it as the product of individual, which is P of xj given ck. Hmm? So now the decision rule is essentially your class is the one which maximizes P of ck into this term. So based upon how you're going to model probability of xj given ck, you have different variants. So if the features are continuous, typically you can assume this is each one you can model it as a Gaussian distribution, normally distributed, then it's called as a Gaussian naive Bayes. If the features are counts, example word frequencies in text, you can call it as a multinomial naive Bayes. If features are binary, the word presence or absence, then it is a Bernoulli naive Bayes. One of the advantages of naive Bayes is it's extremely fast, works well with high dimensional data. It's a good baseline for a lot of problems. The cons being, of course, the independence assumption, which rarely holds in practice, and also the probability scores are not poorly calibrated. One of the most common use cases for naive Bayes is in spam classification or text categorization. So the next simple baseline classifier is called as the k-nearest neighbor, which, while it is simple, is one of the most powerful kind of a baseline that we can try for any problem. Yeah. So the idea is pretty simple. So we classify a point by which majority vote to the k nearest neighbors. Let's say I have a training data set of 1,000, like million points. So for each one has, think of it as a point in a d-dimensional space, right? So for any new point I want to classify, what I'm going to do? I'm going to take that point and I'm going to find which are the nearest neighbors of this, or let's say k nearest neighbors of this. And based upon the decision of the k nearest neighbors, I'm going to take a majority vote of the labels on each of those nearest neighbors. So for example, if it is a regression problem, I can just average the values. If it's a binary classification problem, I can take the majority vote, right? and give you what is the probability of the true label for that particular new instance. So the how do you define an nearest neighbors depends upon the distance metric you use. Most commonly used are like the Euclidean distance metric, or you could use the Manhattan distance metric, or which is the Minkowski distance metric, or also known as sometimes people use the cosine similarity. Yeah. The choice of k depends upon decides your model. If k is small, then example one, then you have a very low bias but a high variance, which leads to overfitting. If k is very large, then you get a very high bias and low variance, resulting in underfitting. Typically, odd k is used for binary classification to avoid ties, and you use cross-validation to find the optimal k. Some practical consideration. Yeah. So, of course, I think the one of the main, I think, well, these are all fine. I think the main thing is in practice, KNN you use with data set which are very large, and you cannot do a brute force k nearest neighbor. So people use something called as ANN algorithm, which are approximate fast nearest near neighbor thumb, and these are based on KD trees or ball trees, different variants of it. Yeah. So this is what, and there is huge family of ANN or FACE are like algorithms available out there, which you can do retrieve k nearest neighbor, approximate k nearest neighbor retrieval extremely fast. So finally, we're going to briefly touch upon SVMs. SVMs, though, were very popular at some point, these days are not that popular. So, but we'll just briefly touch upon what is the core idea of SVM, and we'll not go into very details into how the algorithm is trained. So the goal is you want to find the hyperplane that maximizes the margin between classes. Yeah. And the margin is defined as the distance between the decision boundary and the nearest data points. The support vector means a data point that is closest to the boundary, which define the margin. Yeah. So there are two classes, which is called as the hard margin SVM and the soft margin SVM, which is called as the CSVM. The hard margin SVM assumes data is linearly separable and it maximizes the margin subject to all points correctly classified. Whereas the soft margin SVM, CSVM allows some misclassification via slack variables. The C parameter controls the trade-off. Large C is narrow margin, fewer violations may overfit. Small c is wide margin, more violations may underfit. So many real problems are generally not linearly separable. So the kernel trick in SVM is where you map the high dimensional space to a high dimensional space where it is kernel separable. So the trick is that rather than doing this mapping explicitly, use a kernel which in terms of the dot products, where the kernel is defined in a dot product in the high dimensional space without doing an explicit mapping. Some commonly used kernels are the linear kernel when it's linearly separable, the Gaussian kernel or the RBF, and the polynomial kernel. And each of these kernel has a hyperparameter you want to optimize. Yeah. So that's sort of the agenda for this part of the supervised learning part of the session. So we mainly covered various loss functions and optimization algorithms. Commonly used loss function for regression being mean squared error, mean absolute error, and Huber loss. Most likely you'll use mean square error, but if there are a lot of outliers, you would use the Huber loss. For binary classification, logistic regression, neural networks, you would use the binary cross entropy loss and its variant for multi-class, which is the cross entropy loss. And for SVM, for example, you would use the hinge loss. Then the evaluation metrics are slightly different from the loss functions, and we sort of discussed for binary classification, true positive rate, false positive rate, accuracy, precision, recall, F1 score, ROC curve, PR curve, and the area under the ROC and the PR curves as some of the metrics used to evaluate algorithms. And for regression, it's essentially mean squared error, MAE, and R square. So, and the way to find the parameters is via various optimization algorithms. And commonly used are the SGD style algorithms. And among them, I think the most popular would be the Adam and the Adam W variants to optimize the loss functions. Along with it, some learning rate schedulers like cosine annealing. And towards the end, we also briefly discussed some very naive baselines that we can try out, which is the naive base, which encodes the base assumption. Along with that, the features are independent. K nearest neighbors, which essentially builds a nearest neighbor lookup using a large on the training data set and retrieves the K nearest neighbors and make a decision based on the majority. And finally, the support vector machine, which internally uses the hinge loss function. Yeah. Thank you.